University of Toronto and Royal Ontario Museum. I'm going to talk about some of my work trying to get at the evolutionary origins of blood feeding in some of my favorite worms. But first I'm going to focus a bit more on the actual blood feeding bit. So blood feeding has evolved many, many times in the animal kingdom, and precisely because they drink blood, blood-feeding animals are super important in a number of ways. So they can be really important pests and parasites of both humans and livestock. As you can kind of see up here, there's bed bugs, sea lice, fluke worms, and hookworms. Probably the first thing that comes to everyone's mind when I talk about blood feeders is that they transmit some of the most widespread infectious diseases, both here in North America and globally. I've just chosen Lyme disease and malaria as kind of two, but you can think of tons more. But it is not all bad. Blood-feeding animals are also natural pharmacies. So anticoagulants from vampire bats and from leeches, have been isolated and used in a medical context to either prevent blood from clotting or to break up blood clots after they've formed. So most of the previous research that's been done on blood feeding focuses, probably understandably, on these arthropods, particularly ones that transmit human diseases, but I'm going to make a bit of a case for leeches. So a lot of you are probably pretty familiar with leeches, especially if you spend time doing fieldwork in wet areas. You've probably had an experience like this unfortunate person up in the corner here. And because of their intense bloodthirst, they've been used for about 3,500 years in medicine to treat pretty much anything you can imagine, from depression to obesity, as is the case with this person here. And this next picture is a bit gory, but it serves to illustrate that leeches are still used in medicine today, particularly to treat or to promote healing after replantation surgeries. And then, as I mentioned, there are several anticoagulants that we still use for a number of medical applications. So leeches are pretty much synonymous with blood feeding, right? But it will surprise you to know that only about half of leeches drink blood. The other half are either macrophages, meaning that they ingest other organisms that are whole or in parts, or what we call liquidosomatophagus, which we use to say that they feed on hemolymph or bodily tissues of other invertebrates. And these feeding preferences have been reflected in the historical classification schemes that we use for leeches. So traditionally, we divide leeches into two different groups. One of these groups has a proboscis, and it contains both blood-feeding and liquidosomatophagus animals. And the other group down here, they don't have a proboscis. Instead, they either have teeth or just like a big leeching, like gaping, featureless hole. And that group is further subdivided into animals that are macrophages or blood-feeding. There's been a bit of research done on the molecular basis of blood feeding in leeches, primarily by my PhD supervisor, Sebastian Fist, and my lab mate, Raphael Iwama. And the prevailing hypothesis that's come out of that right now is that there was a single origin of blood feeding in leeches. But it's kind of hard to say much about evolution in this group because we really don't have a good understanding of how leeches are related to each other. And that brings me to the goals of this project. So, what I wanted to do here was twofold. First, I wanted to infer the first comprehensive phylogeny for leeches, and then I wanted to use that tree to trace the evolutionary history of blood feeding in the group. So the first thing I did was assemble a data set. I went to GenBank, and I ended up with a data set comprised of 2 nuclear and 3 mitochondrial loci. In total, I've got over 500 terminals in this tree, representing over 300 in-group species from all of the known families of leeches. And as you can see here, that amounts to about 50% of known diversity. Once I had my data set, I ran a bunch of trees using different optimality criteria, and then I evaluated support for these various criteria using, or in addition to some a priori hypotheses that reflected that traditional classification scheme using IQ-tree. And then once I had that tree, I did a bit of ancestral state estimation on 2 discrete characters, diet and feeding apparatus. I used 2 different frameworks here as well. So I used phase traits to integrate over the topological uncertainty that remained, and of course account for divergence times between lineages, which is going to be especially important here because we have a couple of pretty species poor lineages. And then I just did like a quick and dirty parsimony thing and mesquite, and this is kind of nice because it is going to help me avoid some of the skew that I might have because of uneven taxon sampling. And also, we don't really understand how the these few genes are going to correlate to the amount of evolution. So it's going to avoid skew based on that as well. And this is what we came up with. So what you're looking at here is my Bayesian tree. This is just collapsed, showing the family level relationships, so all the collapsed lineages are represented by triangles. The red bars denote nodes that have posterior probability equal to 1, and the orange bars are ones that had 100% bootstrap support in the maximum likelihood analysis. And then I just illustrated the 5 major suborders of leeches on the right. So I would love to talk about this tree like ad nauseum, but I can't, so I'm just gonna draw your attention to 2 different things here. So the first is that we're able to robustly resolve relationships between pretty much all families, and I say pretty much because there's like this horrible polytomy within herphobiliforms, but that's okay. The relationships that we could resolve are robustly supported, and they are also robust to different methods of inference, so that's quite promising. And then finally, this is not at all consistent with that traditional classification scheme that I told you about. So these 2 suborders up here that have a proboscis are paraphyletic, and if I map the blood-feeding families on the tree, you can see that lots of families that contain blood feeders are more closely related to non-blood-feeding lineages than they are to each other, which is not what we expected, and it's pretty weird. So what's going on here? Well, now that we have the tree, we can start to answer that question. I'm going to take a second to walk you through what's going on here because it's a lot. On the right, this is that same Bayesian tree that you were looking at with the families collapsed, except for those families whose members have more than one dietary state. Those are expanded just so that you can see all of the transitions on the tree. And the branches are painted according to the results of the parsimony ancestral state reconstruction, or estimation. And on this side, these are Violin plots showing the results of the Bayesian ancestral state estimation. They're for each of the nodes that are numbered on that tree, and those numbered nodes are ones where the highest posterior density interval, or HPD, for one state overlapped with at least, or the HPD for at least one other state. Importantly, the Bayesian and parsimony ancestral state estimations don't disagree with each other. So what we have here is this really nice way of quantifying the uncertainty that we have. And first, I want to draw your attention to these 5 plots up here at the top, which are super uncertain. These represent the 5 deepest splits within the tree, and what this is showing you here is that I have really no good estimate of what the ancestral leech may have fed on. So the topological support for these nodes is really strong, and to me that just indicates that the data don't really contain a ton of signal. So even though we can't really figure out what's going on in the ancestor of all leeches, there is some really interesting stuff going on here. I want to draw your attention to this node here, which is the most recent common ancestor of all of those leeches that don't have a proboscis. And if you check out the Violin plot here, you can see that there's pretty unambiguous support for the idea that this leech was macrophagous and not blood feeding. I say unambiguous because the HPD interval that's just shown with those white bars doesn't overlap with HPD for any other state. So I'm going to go ahead and say this is probably not a blood-feeding animal. And if we look a little bit more shallowly in the tree, this is the most recent common ancestor of the Hirudiniforms. That's the lineage that includes all of the medicinal leeches. And you can see that the support for the idea that this was a blood feeder is pretty high. So even if we're super conservative and we say that the ancestor of all leeches was blood feeding, we still have evidence for at least 2 independent origins of blood feeding within this tree, which is really, really cool, and it doesn't jive with what we thought earlier. But I also kind of don't want to oversell this, because you've probably noticed that even though the support for this loss of blood feeding and the common ancestor of leeches without a proboscis is unambiguous, it's not super strong. The HPD centers around like 61%, which is less than ideal. So we wanted to look at other traits to see if we could get an idea of what was going on in this node, other traits that might be ecologically correlated, and that is where the ancestral state estimation of the feeding apparatus comes in. So this is really similar to what's going on in the previous slides. Again, we have that Bayesian topology with all of those families whose members have more than one different type of feeding apparatus expanded. And this is super busy because I coded this as a 12-state character. again, there's a lot going on here, but the only thing that I really want to draw your attention to is, again, that same common ancestor of the leeches that don't have a proboscis. And on the bright side, the most likely ancestral state at this node was agnathus, or jawlessness. And this supports our idea that these animals would likely not have fed on blood, because if you can't pierce the host's skin and access the blood, you're not going to be a very effective blood feeder. But these results are super ambiguous. The HBD intervals for every state are pretty much non-zero, and I think part of what's going on is that these might be like sapping support away from other hypotheses that are probably more strongly supported by the data. I used really uninformative priors here going in, but there is kind of a bright side, and that is that I have some pretty good biological reasons to think that some types of transitions are going to be a lot more likely than others. So I'll be able to use more realistic priors and further analyses going forward, and hopefully get a better idea of what's going on here. So, what have we learned? First, we've got the first comprehensive phylogenetic hypothesis for leeches, and we've been able to robustly place pretty much all of the families that we know of, which is really great. And our ancestral state estimations of diet and feeding apparatus support at least 2 origins of blood feeding in this group. There are a lot of other ecological and life history characters that also support this hypothesis, and I don't have time to get into them, unfortunately, but if you want to hear more about one, hit me up. More excitingly, what can we do with this going forward? So like I said, I want to try and get a better, try and refine ancestral state estimations using more realistic priors. I also would really like to try and put some dates on this tree so that there are a lot more different methodologies open to me. But kind of more importantly, I can now address some of the questions I've been thinking about for years, including whether transitions in diet drive the diversification of anticoagulants, which is something that my lab mate Rafa and I have been working on. Whether dietary shifts are correlated with changes in feeding apparatus, which would be pretty cool, although Matt Pinnell's talk this morning has me worried. And whether blood feeding is associated with increased rates of diversification in these species, and also whether diversification follows patterns of vertebrate diversification, because that might be really neat. So I'd like to thank you all for being here. I'd really like to thank a lot of my co-authors and my lab mates and the other folks who have helped talk me through a lot of these problems. And I'd like to acknowledge my funding sources and take some questions.
Super interesting, thank you. I'm just curious about the models that you use in the leeches space.
Yeah, I just used the reverse jump MCMC process, and I ran that on the entire exterior distribution of trees that was used to generate my Bayesian consensus tree. And going out, I just used totally uniform priors. We just got convergence, and that's what I got. So I'm going to definitely be refining those going forward.